So, welcome to massive open online course on chemical process intensification. So, in this lecture we will discuss about the intensification in reactive system. In the previous lecture we have discussed the various aspects of process intensification based on the mixing characteristics. So, along with that mixing characteristics, how the process can be intensified in the reactive system, we will discuss something more about that. So, this lecture includes the mechanism of process intensification in reactive system. You know that nowadays increased legislation on emissions and the use of waste and also disposal of the waste, and also the need for businesses to remain highly competitive environment and to demonstrate its product to the society. You know that the some important reasons for the drive towards the greener processing. So, greener processing nowadays is coming because of that environmental impact of different byproducts which are coming during the reactive system. And for that you have to take some measurement as per legislation act that you have to produce the byproducts or products in such way that some hazardous materials which are coming out as a byproduct should be minimized or should be removed. So, today ecology actually demands that thinking of that process intensification, how it can be done to reduce that hazardous materials which is coming out as a byproducts in reaction system in a particular process. So, nowadays the peoples are thinking a greener way, and how to actually people can live in greener way, that is greener living and also in a greener environment by developing some process in the chemical industry whose products which are being actually used in our daily life. So, the ideal process in which byproducts are reduced or eliminated altogether at the stage of reactions. So, in that case if you are developing some process where byproducts which are coming at its reaction stage can be actually eliminated or reduced rather than removed after they are formed, and that concept should be developed, and that concepts are called that waste minimization concept at source. So, this is the you know that thinking nowadays to shift the conventional process to the greener process, where you can get that more greener living, more greener thinking and greener environment, and also greener that sustain the development in the society. And the successful implementation of the greener chemical process actually relies on that development of more efficient catalysts for the synthetic chemistry, because whatever products will be produced by a certain process, you know that chemistry works behind. So, as per synthesis by the chemistry that the products that you have to develop some more efficient catalysts for the synthetic chemistry, so that you can get less number of hazardous materials for that particular synthesis process. And another aspect is to develop the reactor and separation technologies which should be more safe and cost effective and also energy efficient. So, you have to implement the greener chemical process based on these two concepts. First is development of more efficient catalyst for the synthetic chemistry, and development of reactor and separation techniques in safe, cost effective and the energy efficient manner. Now, main target of that green processing is to diminish the environmental bad impact that is processed by the chemical industry. And one of the ways which can be made possible is by minimizing the scale of reactors operating that will be ideally in continuous mode. So, that more rapid heat and mass transfer even in mixing effects and plug flow behavior can be achieved, and also for high selectivity in the optimized reaction processes can be achieved. So, the target of the green processing that actually includes the way of thinking of that minimizing the scale, or you can that that minimizing the back mixing in the operating system, or making the plug flow system where you can get that products with high selectivity and at an optimized reaction process in a continuous mode. And you know that there are several reactors are being developed nowadays industries based on that, you know that optimization of this separation techniques, and also you can say that reaction systems. So, in that case some intensified reactor technologies for the greener processing are being developed, and in that case you have to use some alternative forms of energy to promote that reactions. And like in that case several reactors here, spinning disk reactors, micro reactors, monolith reactors, oscillatory flow reactors, hybrid that reactors or separator systems, like the reactive distillation, reactive extraction system. Those are important phenomena where that intensified reactor technology can be used for the greener processing by using that that alternative forms of energy to promote that reaction in its into the reactor system. Now, what should be the role of reduction in scale? It generally allow the reactions to proceed at their inherent rates, and also rapid mixing environment that afforded by the low reaction volumes that should enable conversion and selectivity to be maximized. Also, you know that if you reduce the scale of the reactor just by making like that microchannel based reactor, in that case a thin film will be produced to enhance the mass transfer during the reactive mass transfer operation. So, the reduction in scale has some role to proceed the reactions in their that inherent rates, and also the reducing the back mixing, and also the increase the mixing phenomena afforded by low reaction volumes, and also conversion and selectivity can be actually obtained at its maximized stage, and also that thin film can be produced to get enhanced mass transfer during the reactive operation system. Now, as of now we know that there are several reactors are produced for the process intensification for this reactive system. Earlier you know that generally that CSTRs are being used for that reactive system. Nowadays it is not desirable because of some reasons, because these CSTRs, that is continuous starting reactors, whatever RTDs is generally we are getting by that CSTRs, that is not desirable, because mass of the material in the reactor will spend too long in the reactor due to the long tail in the RTD profile, and will consequently be that overcooked sometimes in the reactive system. And the main problem with this is that it allows competing reactions to become more significant, and also you can say that it will not give you that desired level of conversion, and mass of the material will be in the reactor for less than that desired residence time, because in the maximum cases for high rapid mixing will give you that in that small scale system If you are having the larger scale, there may be that radial distribution of the liquid element, and in that case that back mixing is sometimes will hinder the selectivity of the, or you can that yield of the reaction. And in that case it is desired to actually reduce that back mixing and getting the higher residence time, and it can be possible only by reducing the scale. So CSTRs are not actually nowadays that much important, because as per process intensification concept, there are several that different types of reactors where these reactions can be carried out just by reducing the size and also making the thin film of the fluid element, through which that mass transfer can be achieved more intensified way. And CSTR can thus lead to the increased by product formation and unsatisfactory conversion. In that case, if you are getting that back mixing, in that case you can get more some other byproducts, and also it may reduce the yield of the reaction. So that is why that unsatisfactory conversion may actually that give you, or you can get by this CSTR. So it cannot be actually suitable nowadays for the process intensification. Now, in contrast of this plug flow condition, you will see that we can reduce that back mixing, and in that case more residence time also can be obtained. Now, each element of the fluid that will experience the same processing history, and also each molecules will spend exactly the same amount of time in the reactor as every other, and it is subject to exactly the same sequence of conditions. And also by that in plug flow conditions, smaller volumes then an equivalent CSTR will give you the advantage of that yield of the reaction. And also in plug flow systems, this will reduce the byproduct formation and ensures that the desired conversion can be achieved. So, plug flow reactors are often preferred in principles. In practice, they are difficult to use at long residence times, above a few minutes you can say, and multi-phase reactions can be difficult. So, all reactors have some advantage and disadvantage, though it has that reduction in back mixing and it can give you the better yield, but sometimes that handling of this micro scale reactors, it is very difficult, and also multi-phase processing also difficult in this type of reactors. So, only for single phase flow it is sometimes okay fine, or suppose in higher scale, even you know that large scale systems also it is not possible. So, some suitable the chemical engineering processes where this plug flow phenomena can be actually utilized as a process intensification, and in that case it will be suitable for that particular long residence time, and also that for a smaller volume handling of that particular processes. And some other processes in reactive systems, some other mechanism also possible to intensify the reactive system in chemical engineering processes, like that centrifugal acceleration is one of the important mechanism by which you can intensify the process, like the centrifugal acceleration that generated on the surfaces of the revolution, that will presents remarkable potential for the intensification. Like in that case, by this centrifugal acceleration you can handle the multi-phase reactions also, gas liquid solid system reactors, whereas the plug flow systems one dimensional system, in that case it is very difficult to handle that multi-phase processes, where in centrifugal acceleration systems it is possible in both 2 and 3 phase systems, like centrifugal adsorber, high gravity technology, rotating pack beds, centrifugal extraction, or that distillation are the some important that technology, and some unit where you can process this multi-phase system at its reaction condition. Now, another important mechanism, it is called ultrasound system for the process intensification. In this case, ultrasonic waves that will generate intense mixing conditions and enhance the transport rates throughout the bulk of the liquid medium in homogeneous systems, and at liquid liquid or liquid solid interfaces in heterogeneous systems. So, which have a direct that positive influence on a chemical reactions. So main important thing is that ultrasonic waves are being used to generate the interfaces between the phases, like if you are handling that gas liquid process or liquid liquid process. So this ultrasonic waves will generate that drop or bubbles where that you can get that interfaces between the phases. So that phase through that that interfaces, this mass transfer system happened. Even sometimes it is advantageous for that some systems where liquid liquid or liquid solid interfaces to be produced in heterogeneous system. It is sometimes that advantageous. Even some only single bulk liquid medium where homogeneous systems to be produced by these ultrasonic waves for gas liquid operation to distribute the gas throughout the liquid medium. In that case, this ultrasonic wave also advantages. And like example, synthesis of nanoparticles of calcium carbonate particles by ultrasound cavitation techniques. In this case, that the immiscible liquid system produce finer droplets, and which can be formed under ultrasonic exposure. Then by mechanical agitation, that creating or generating surface area for mass transfer. And in that case, chemical effects due to ultrasound in that case arises if the chemical compounds in the processing medium can fracture into reactive intermediates such as free radicals to be produced under the very intense local temperature attained in the bubble cavities. So this is the way, and here one synthesis process is given in the slides by which you can produce that calcium carbonate nanoparticles. Here in this case, pulse controller to be used to generate that ultrasound waves by sonicator probe, and in that case some input and outputs are given in this slide. So please go through this process by which you can get this calcium carbonate nanoparticles. Here two solutions are to be used. Solution 1, solution was ammonium bicarbonate and waters, and with SGS, and also solution 2, calcium chloride and water plus SGS to be used in a that distilled water under ultrasound condition in presence of some surfactants, so that you can produce more interfacial area there in the reactor. And after that, if you get these solutions after this sonication reaction, then solution of calcium carbonate nanoparticles will be produced, and if you mix some TEVS and acetone in that solution, you can get the that agglomeration, and then you have to de-agglomerate that calcium carbonate nanoparticles to get its that calcium carbonate with TEVS chains. So in this way, you can do some reactions in this ultrasound environment. And benefits of this ultrasonication assisted reactions are the increase in both reaction speed and yield in an extensive range of heterogeneous and homogeneous systems, and it will lead to gentle processing conditions, that is that ambient temperatures and pressures, reduced solvent use, and also higher energy efficiency. It will also give the benefits of the use of environmentally that benign reactants and solvents, while retaining or even enhancing the reaction rate under ultrasonication. So in that case, you will see that main important aspects of that ultrasound is that to generate the interfacial area through which that reaction and mass transfer will be happen parallelly. Now, another important mechanism, it is called that electric fields. You can apply the electric fields to intensify the reaction. In that case, again that by this electric fields you can produce large interfacial areas, and by producing small droplet formation. In that case, higher degree of stable emulsions can be achieved, and also it can enhance the overall rates of reaction in immiscible liquid systems. So, formation in that the droplet formations, small droplet formations will give you the larger interfacial area in electric fields, and based on which you can intensify the reactions by producing that stable emulsions in the system. Like here example, remote control of anion pi catalysis by electric fields, which is one example there. And another examples of electrostatic fields which are being used to intensify the dispersion of the aqueous phase into the oil substrate by creating large interfacial areas between the reacting species, like enzymatic hydrolysis of triglyceride esters to yield free fatty acids and glycerol. In that case, you can produce droplet of that aqueous phase in the oil substrate, and also produce the large interfacial area between this reacting species by this electric field. So, in that case enhance the overall rate of reaction at relatively modest temperatures and pressures. And also the combined effects of the electric and centrifugal fields on hydrodynamics in thin film flow in a spinning disk reactor have a that greater potential to further enhance heat and mass transfer and reaction rates in thin film processing. So, that not only producing that interfacial area by making that that immiscible phase particles, but you can increase the heat and mass transfer or reaction by producing the thin film without producing that droplet or bubbles there also. So, in that case combination of electric and centrifugal fields that can be used for this hydrodynamic to produce that thin film flow in a spinning disk reactors. Another important mechanism, it is called that microwave using for the intensification of the process in chemical engineering process. Like that microwave sometimes assist the process, where microwave expose result not only in higher rates of reaction than conventional heating methods, but also in better product quality through improved selectivity. Now, in that case that small scale batch and continuous reactor systems with microwave irradiation capabilities are commonly used in commercial sectors nowadays. So, some that microwave assisted synthesis has some advantages, like that some reactions are being happened by this microwave system, microwave assisted synthesis process, like reduction reaction, like coupling reaction, cyclization reactions, and also that multi-component reaction, condensation reaction, even isomerization reaction, even hydration of nitriles. All these reactions are based on this microwave assisted synthesis, where you can get the intensification compared to the conventional process. Now, if you use the sunlight also, there may be a that intensification of the reactions, like certain compounds that can be affected by sunlight to give materials with the same chemical composition, but very different physical properties. Like styrene is converted from a liquid to a glassy solid when it will be exposed to the sunlight. So, in that case that photochemistry, that is potential of photochemistry, has been widely demonstrated in industrial sectors in a number of reactions, like such as production of caprolactam that is used in the manufacture of nylon 6, and the formation of vitamins D2 and D3. So, sunlight assisted that reactions is also one of the important figure in the intensification of the process in chemical industry. Another important mechanism, it is called photo initiation. In that case, small molecules that are sensitive to the light, in that case photo initiators are being used to make these small molecules to sensitive to the light, and upon light absorption on the molecules, they undergo photochemical cleavage to produce reactive species, either free radicals, or you can say that Bronsted or Lewis acid it is called, that will interact with the active components in formulations. So, it is an inherently you can say that a clean process and requiring only the reacting molecules in order for the reaction to be activated. So, photo initiation is also one of the important process intensification in chemical industry, where molecules are being actually undergo the photochemical cleavage to produce the reactive species by absorbing the sunlight or some other light also, not only sunlight, that you can say some that common light also you can use for that. So, it is an inherently clean process where you can produce the products without having so much that hazardous materials, and in that case requiring only the reacting molecules in order for the reaction to be activated there. Now, the irradiation by a specific wavelength and therefore a well defined energy input in the form of photons is required, and which will allow only certain reactions to be targeted, thereby reducing byproduct formation and costly downstream separation processes. Since activation is by light, the ambient operating temperatures can be utilized, which not only reduce the thermal energy consumption, but can also result in better control of the process, especially if is there any side reactions are there or not, and can be minimized at lower temperatures in this case. And this is particularly relevant for that polymer processing, where low temperatures generally result in like better tacticity control of the polymer, reduced transfer efforts, and also which can be a cause of excessively branched macromolecules, and in this case minimal thermal degradation risks for the polymer formed can be achieved. So, that is why particularly it is relevant for this polymer processing or this photo initiated that polymerization. So, in this case you will see the schematic of this photo initiated polymerization given in the slides. Here light sources are being used in a photo initiator. After that reactive species will be formed based on this absorption of this photon, and free radicals or ions will be formed, and then the monomer, this polymer change will be formed based on this reactive environment. Now, intensification by milli or micro channel structures is one of the important aspects of this process intensification that already we have discussed, that producing the plug flow phenomena and the residence time, intensity of the residence time, and also reducing the back mixing there, and it is being important. So, that milli and micro channel structured reactors are being used for the intensification of the process. Like here typical dimensions of this milli or micro channel based reactors are 10 to 100 millimeter for milli channel and 0.5 to 2 millimeter for micro channel reactors. And in that case reactions spaces in the form of channels of the various shapes can be actually developed or can be used, and also that more precise control of diffusion can be done, heat exchange can be actively obtained, and retention and residence times and flow patterns in chemical reactions can be achieved based on this milli or micro channel structured reactor. And here in the slide some diagrams are shown here, the some that how this micro channel based or milli-channel based reactors are being developed. Now, intensification by these milli or micro channels have some advantages, like the diffusion time scale is greatly reduced in this micro channel based reactor, efficient micro mixing in fast reactions where micro mixing times of the order of milliseconds can be actually obtained, and which are required for this particular reaction system. And it will provide very large interfacial areas for efficient contact between reactive streams in the channel, and it can be achieved through a number of passive techniques. For example, the use of miniaturized static inserts which continuously split and recombine the flow streams or you can say of turbulent collision of the injected streams which are being used for that reaction. So, you can say that this micro channel based structure will reduce the diffusion time scale, and also plug flow phenomena, efficient micro mixing, and also you can say that large interfacial area which is being produced in the channel, and it can be actually also achieved by collision of this turbulent collisions of these injected streams which are being used. And like hydrogenation reactions, say nitration reaction, and a simple acid base reaction, all of which require rapid mass transfer in order to keep pace with the inherently fast reaction kinetics. So, in that case these type of reactions are suitable in micro scale reactors like milli-channel or micro channel based reactors. And in this case since you can produce that plug flow phenomena, so this plug flow behavior that gives control of RTDs in micro or milli-channel reactors, and that can be achieved by introducing, that is segmented flow via a second phase in the flowing systems, and very good control of highly exothermic reactions in small diameter channel reactions is also possible due to the extremely high surface area that is produced during the flow in the channel, and also that the surface area to the volume ratio is high, and it is up to 50,000 meter inverse when compared with conventional starting reactors which are being used for reactions in earlier stage. And another important mechanism, it is called membrane reactor development, by which you can intensify the reaction system, and membranes that are sometimes permeable to only one of those products are used to remove this product in situ, thereby you can overcoming the equilibrium constraints. So, equilibrium, to that achieve that smooth equilibrium condition, you can also do that intensification reaction, or you can that membrane reactor you can use for that particular reactive systems, and it will provide you simultaneously producing synthesis gases for the ammonia and liquid fuel in one membrane reactor as an example. And these membrane reactors have often been used to bring that equilibrium reactions to completion. So, for the complete reactions you can do this process in membrane reactors. In that case that permeability should be one important factor by which you can assess the degree of reactions by this membrane reactor. Intensification by reactive extraction is also one important nowadays, that reaction as well as extraction both will be simultaneously carried out, that is called integrated system. So, this is a separation process in which reaction is used to cause a product to move into a different phases where you can separate those products, and this is usually between two liquid phases, normally organic and that aqueous systems, and also you can say that it can be between solids and liquids. So, there should be multi-phase systems, and this is often a way of overcoming equilibrium limitations. So, if you integrate the system of reaction as well as extraction, you can use that reactive extraction systems, where you can get the intensification for the separation process, as well as you can reduce the unit and simultaneous occurrence of the reaction and extraction, and also energy efficient it will be processed, and you can overcome also the limitation of the equilibrium of the reaction. So, here one example is given in the slides, that phenol extractive in a reactive environment, phenol extraction. So, in that case reaction 1, where sodium phenolates to be produced by that sodium hydroxide from this bio oil, and after that you have to do the filtration, where the sodium phenoxide is being actually separated, and after that there will be reaction with that sodium phenoxide, and along with that some alkaline solution, and with hydrochloric acid solution with a certain percentage at a certain pH value, and after that whatever products is coming out, that sodium phenoxide compounds which will be actually reacted with hydrogen chloride, that will give you the phenols and sodium chloride at pH 5, and after that you have to extract that solvents, liquid extraction, that will give you the separation of these products to its certain degree of purity. So, in that case reaction and extraction both will be carried out in a single unit. And also that intensification by reactive distillation is also another aspect of that, getting the process intensification simultaneously considering that reaction and distillation. In this method, distillation column has a second function as a reactor, which removes the reactor from the flow sheet. And the greater advantage usually lies not in reducing the number of unit operations, although this can be a significant benefit in the plant, but in overcoming the equilibrium limitations of a reaction by removing the product through distillation, like that Eastman processes of methyl acetate synthesis, where this reactive distillation systems are being used. Supercritical operation also one of the important aspects of that process intensification in chemical processes, like a substance whose temperature and pressure are above their critical values, and using that the properties of that supercritical fluids, you can use that for the process intensification in reactive system also. Like in that case supercritical fluid has some characteristics like low viscosity, high diffusivity, and density can be varied continuously, and in that case extraction, reaction, separation and preparation all can be done by this supercritical operating condition. In that case extraction of caffeine from coffee beans can be done by the supercritical extraction process. Extraction of essential oils also are being done nowadays by the supercritical process, supercritical method, and reaction like oxidation, synthesis and degradation reactions using supercritical water and enzymatic reactions are being carried out by this supercritical fluid system. Separation and preparation also can be done. In that case preparative isolation of chiral compounds, and also the analysis of polymers and hydrophobic compounds are being done based on this supercritical condition. A key advantage of performing reactions in the supercritical carbon dioxide, for example, is that separation of the solvent, the carbon dioxide, from the reaction mixer, that becomes facile, and it does not require a separate unit operation. So, this is the advantage, and instead you can say that all that is required is that the pressure be released to the necessary degree for the reaction mixer to come out of solution. So, this is important for this supercritical operation based on which you can perform the reactions in supercritical carbon dioxide for the separation of solvent from the reaction mixer, and without using that separate unit operation. And that other important aspects of the process intensification, that you can have the intensified process by more effective mixing, like more effective mixing observed in continuous reactors often lead to higher rates of reaction, which lead to smaller reactors for the same production rate, and when the reaction is mixing limited, but it often occurs at larger scales. In that case, good mixing is difficult to achieve at a scale which limits the reaction rate. And when reaction times are reduced by conversion from batch to continuous, the reaction mixers has to be held at the correct temperature for a shorter period of time, which reduces the heating duty in that particular reactive system overall. So, I think we have discussed, we have that learned something about the process intensification mechanism based on this that reactive environment, how it can be done, how actually the reduction of back mixing will help that that reactive system for the process intensification reduce the limitations of the equilibrium, and also how we can that control the residence time of the phases, and also that mixing characteristics, and also how to produce the interfacial area by different that mechanism like electric field, or that cavitation process, or you can that if you can use some photon systems in that photo initiation method, where you can produce that interfacial area and also activate the species for this process intensification in reactive systems. So, several that mechanisms are discussed in this lecture. So, you can have more information. I will suggest for further reading of these textbooks that is given in the slides, or in also that in the course handout there in the course system. So, thank you for this lecture today.